Alright guys, welcome to the notes. Make sure you're filling in the guided notes as we go, and we'll be done with this one pretty quickly. So we're going to talk about weight and mass tonight. These are kind of, once again, two words that commonly get misused, and this is because in science we have definition that is slightly different than what people in society use. So hopefully by the end of this you'll be able to differentiate between the two, and when we come into tomorrow we'll have a lot more discussions about it. So let's start. So imagine you're on Mars. Is the amount of matter that makes you up different? Take a second to think about that one. And clearly the answer should be no, that this amount of matter that makes you up now would be the exact same amount of matter that makes you up on Mars. But what would be different is the force pulling you downward. So what we typically call that force is the force of gravity. And are those related? In other words, is matter related to gravity or is weight related to gravity? And that's kind of the idea you need to keep in your mind, and hopefully we'll have that answered by the end. So before we do that, let's talk about how you actually calculate weight, and we'll come back to this later. So I gave you an equation up here, and here's the equation. Oops, that's terrible. But we see that Fw, notice I write it with an F because, as we're going to see later, weight is a force. So Fw equals mass times g. So Fw equals m times g. Well, if we go down here, we know that all forces in general look something like this. Force equals mass times acceleration, right? We've seen that. Well, we're just slightly changing that equation. And now we're saying that the force of weight, because remember, weight is a force, is your mass times the acceleration due to gravity. And then we call that g right here. So really, are we changing the equation F equals ma? Not at all. We're just explicitly using the acceleration due to gravity. So one big misconception is that weight is typically measured in newtons. And why is that? Because like I just said, weight is a force. So weight is measured in newtons, not pounds like people always say. So if you're measuring it in pounds, you're actually not using the scientific notation correctly. So I gave you an example problem. Why don't you sit down and try to do this one real quick. Go ahead and pause it, and we'll come back to it. Pause it now. Alright, since you've paused it, let's go over it. It says, if you have a mass of 22 kilograms on Earth, and remember, Earth's gravity is 9.8 meters per second squared, what's your weight? Well, you know that Fw equals m times g, right? Well, I gave you the mass. Mass was 22 kilograms. And I gave you g, 9.8 meters per second squared. That's always here on Earth. Now, if we're on a different planet, that's going to change. So I think everybody's good except for a few of you. You know who you are. So, let's figure it out. F equals m times g. So, my m was 22 kilograms, and my g was 9.8. What's that come out to? I don't know, I don't have a calculator, but you know what I do have? Is the answer on the next slide. I win. So, here we go. 22 times 9.8 is 215.6 newtons. If we look down here at the next one, very similar again. You just had to rework it slightly because what did I tell you? I said you have a mass of 22 kilograms on Mars, but I also told you Mars has 1/3 the gravity of Earth. So in order to figure that out, you needed to take g, or 9.8, and multiply it by 1/3. Gives you 3.27. That multiplied by the mass is 71.94 kilograms per meters per second squared. Whew, that's a lot to say. Or you just say newtons. Either way, it's the same. So if you don't understand that, don't worry. We're going to hit it again tomorrow, but it's really just simple. All we're saying is Fw equals m times g. And ignore this line. That was a stupid line. Moving on. Let's talk about mass more specifically here. We've used mass before, okay? Mass is the amount of the amount of matter that makes up an object. I kind of left out the makes here. Sorry about that. All right. It's measured in kilograms. Now, this is really, really important. Like I said today in class, when you use that Fw equals m times g, that m equals kilograms. And if it's not in kilograms already, you've got to convert it. So, as we were saying earlier, like Marvin the Martian in the beginning, your mass will be the same on Earth or on Mars. I mean, think about it. That doesn't make sense, because the atoms that make you up are going to be the same. The same amount of atoms you had on Earth are going to be the same amount of atoms you had on Mars. Unless, of course, you were in some tragic accident and you lost an arm or lost a leg, but God forbid, it'd be the same. So you have the same amount of matter everywhere, no matter where you are. That being said, your weight will be very different, because weight is a measure of the force of gravity acting on your mass. In other words, once again, Fw equals m times g. So let's think about it. Yes, weight is dependent upon mass. That is true, but it is also very dependent upon gravity. So if you're in an area with less gravity, what does that mean for your force or your weight? Well, it'll be less. Inversely, if you're in an area that has a high gravitational force, well, your weight would be more. So mass is the same everywhere regardless of the gravity. Gosh, man, I am really bad at that tonight. But your weight will change because gravity changes, and gravity must be noted when you're calculating weight. Like I was just saying, here it is. You can see it a little more graphically here. Got my little astronaut guy here on this Earth. His mass is 120 kilograms here. But his mass is also 120 kilograms here on the moon. Well, if you think about it, force of gravity pulling him down to the center. Force of gravity here on Earth is much, much more when compared to there on the moon. So, if all of a sudden I have a lower g here and I have a higher g here, when I plug that into Fw equals m times g, well, if my g goes up, my weight goes up. If my g goes down, just like it did here, my weight goes down. So what's the world's quickest weight loss plan? Go to the moon. No, seriously. You lose weight. But do you lose mass? Of course not. Talk about friction. And this one clearly got in the way a little bit here, but that's okay. So friction is a force that results from the relative motion between two objects. Well, key word here is motion. In other words, if you don't have motion, you don't have friction. And friction also works against and slows motion. In other words, let's draw a picture here of Mr. Sneed. Here I am. Yes, I drew my bald slot. Let's say I'm walking this way. My frictional force would be in the opposite direction. Notice these are vectors, so the length of the line, my force is much larger here, where my friction is a smaller force here, acting in the opposite direction of my motion. So, friction is a force that works against and slows motion. If we look at this, oh, come on, that's awesome. Think about it. Polar bear falling, lack of friction, get it? We can talk about it. Friction's useful. We need it. In other words, friction between our ground. If it wasn't there, what would happen? We'd look like this polar bear the entire time. We'd be slipping. Friction while we're driving. Why do more accidents occur in the rain? Well, because there's less friction. Brakes. If you want to stop your car, you got to have friction. Now, that being said, some friction is unwanted. Overheating of the machines. That's always due to excess friction. Maybe you didn't have oil in your car. Okay, it wasn't lubricated well enough. Slowing down when you don't want to. Friction. And friction makes moving objects heavier. So it gives lazy people an excuse not to move things. So friction's good, but it also is sometimes unwanted. Quick recap. Gosh, these pictures are all in the way. Sorry about that. Gravity pulls everything towards the center of the Earth, and it pulls it here on Earth at 9.8 meters per second squared. We'll talk about if that's completely always true. Weight is a measure of the force gravity pulling on an object, and friction is a force acting in the opposite direction of motion. We're going to tie all of that together here at the end. This is a quick recap from today. You can think about, remember this Rebecca Black video? Okay? This is two of our classmates arguing who deserves it more. One pushes this way, one pushes the other. Well, if this person only applies 18 newtons and this one applies 20, well, then that one is -2. Now keep in mind, no, that does not mean this person was negatively weak. We just said it went that way, and this way was positive, therefore the yellow line had to be negative. So what we're going to do is tie all of that together in what we call our free body diagrams. This is our honors edition for the unit, so welcome to honors, boys and girls. This is what you get. Pretty simple concept, though. In free body diagrams, we're going to use a box to represent anything. So here's my box, and my box is sitting on the table, right? Well, free body diagrams are going to include all of the forces acting on that box. So, luckily for us, I have one drawn on the next one. Here's my box again, okay? If we look at our box, here's the center of the box. We have a line going down right here. This line represents my weight. You could even draw that FW if you wanted. Notice it's in newtons, right? Because all forces are in newtons. We have a line going this way, pushing up on the box from the table, and this is what we talked about today, was our normal force. And then we have this guy, FF. That would be our frictional force. And then we have an outside force right here of 8 newtons. We can call that our push or our pull. I have a big question for you down here. Is this box moving? If so, which direction and with what force? So what I want you to do is look at our drawing here. Now that I made it a mess, you can even rewind and go look before I made it a mess and think to yourself, would that box be moving? Do that now. Alright, if you've done that, you'll see that weight at 6 newtons and normal force at 6 newtons cancel each other out, especially considering the fact that they're going in perfect opposition of one another. Well, if we look at this force, we have 8 newtons to the left and we have 4 newtons to the right. Do a little basic math here, and that means 4 newtons to the left. In other words, our box is moving to the left due to the overall net force of 4 newtons. So is it moving? Yes. And with what force? 4 newtons. Yes, that's an N, believe it or not. It's the world's worst N. This way. Remember, guys, you're not supposed to be pros at the end of this, but at least you have some background knowledge. And when we come in tomorrow, we can spend a lot of time on these free body diagrams. I have some cool demos. I have some really cool, almost a video game that we'll look at. Watch some videos. Cats in Space. Yes, I said Cats in Space. We'll see you tomorrow. It's amazing. Watch some more sports science. And we have some mini labs. So, a lot to do. Very little to talk about. Have a good night, guys.